Hey, what's up and welcome back to the channel. This is the Prokon Geek, and in today's video we continue with the base design module from the concrete design suite that is coming from Prokon. So what we're going to do is we already have the base design module up over here, and we need to continue with it, looking at how we input the data, interpreting it, and also some of the theory as we continue with it. So the only way to continue with it is to dive in and start looking at an example as we continue further with this module. So without wasting too much of your time, let's just get right into the video. Okay, so first things first, we need to understand or look at the geometry input for this particular module. So remember, we have the geometry and material properties input, then we have the load cases and stability criteria sections, which we talked about in the previous video, but now we're going to talk about them in depth. So to better understand these things, we need to go to AutoCAD, which is one file that we already have. So if you want this file, it's going to be in the description link below, right? What we can do is we can always choose, let's just go to the tutorial layouts that we always had right in the beginning. So in this case, we're going to be trying to design one of these bases, and in this particular, the base is just the same, it's the same throughout. In this case, it's 1000 by 1000. So this is what we're going to take note of and then go back to the base design module. So once you're back in the base design module, this is what you need to do. So remember the base length. So this will also help you understand what is A. In our case, it's 1000 millimeters or 1 meter. So we're just going to put 1 and 1. And as you can see automatically on the screen, it updates to show you that in plan, this is your base and this is what you have. And if you go down, this will show you in elevation. But in elevation, it does not have any thickness because we have not entered it as yet. Now, if we go back to AutoCAD, what we would do is we just want to see what column we want to design for. In this case, this is going to be 300 in this direction, and it's going to be 230 in this direction, right? This is getting a little bit clustered. So what I'm going to do is I'm just going to MA. Let me just MA, select this, make this a little bit less clustered so that we are able to see or visualize what we are talking about. So it's going to be 230 in this direction. Let me just push it to this point. Okay. And let me just push it to this point as well. And it's going to be 300 in this direction so that it's clear to see. So what you have to do is, this is what you do. You enter the base length A and the base length B. So it is shown on the screen, but I just wanted to show you so that you better visualize. So remember, A is going towards or parallel to the x-axis and B is parallel to the y-axis. Next, what you have to do is to input the loads for the columns, right? Or rather the geometry of your columns. In our case, we only have one column, so we're going to be using one column, which is column 1. In the case where we had two columns, we will need to use column 2, the column 2 section. So in this case, the column what we need to go back and check. It's telling us we have a 300 and 230 column. So what are we going to do? In this case, it's millimeters, remember? So this will be 0.300. And now remember, if you only put C and don't put D, you'll be designing for a circular column, right? But in this case, you want to put rectangular column. So what you're going to do is 0.230, right? In this case, as you can see, you have modeled it nicely for you. So remember, C is the distance or the length that is parallel to the x, and B is D is now the length that is parallel to the y axis. So in our case, parallel to the x it's 300, parallel to the y is 230. So that is why we put 0.30 because this is in meters. Remember, I'm using millimeters, and just divide by 1000 to get in meters. So we have 0.3 and 0.230. So one thing that you need to notice is, once you put your dimensions, your column will always be positioned at the center of the base, because this is the ideal position or location that you would want your base to be in. This will always be the case unless you enter non-zero values for E and or F. So what we will do is we will look at that example when we look at one of the bases that we have. In this case, what we could is, remember, we have those bases for the strap beams which are not centered at the center of the base. So once we're going to be designing this or looking at the example for this one, because we're going to look at the one way it is centered and one way it is not centered, so we will better understand E and F when we look at this example. But for now, we're just going to be using the one way it is centered, because that is the first example that we just need to look at. Next up, when you are done and you've put in A, B, C, and D, and for this case, we're leaving E and F as it is, or you can just put 0 just to remind you that it is definitely going to be 0. Now, the next thing that you would want to do is you want to start putting in the geometry. You're still putting the geometry as well, so you're still doing the geometry, remember that. Now you need to look at the stub column height and the base depth. For the stub column height, in this case it depends on the situation that you have, but in my case I'm just going to get this one, which is there. So we're just going to say this one is going to be 1500. So let me just MA, right, so that this one matches this. So it's going to be 1500. So what you need to do is you need to come here and say 1.5, because remember this is in meters, whilst previously we were using millimeters. Now what is the depth of your base? In this case it's going to be 500 millimeters or 0.5 meters. So all you have to come in and put is 0.5. So what is going to be the soil cover? In our case, remember the soil cover is going to be the cover to where you have the datum ground level. So in this case the datum ground level is going to be, and the soil cover from the top of the base now is going to be also 1500, because that is equal to the length of the stub column as well. But in the case where maybe the datum ground level was at a level that is, say, less than 200, in this case what we can do, we can always shift that, because what we can do, let me just do this, forgive me, all right, sorry. What we're going to do is we're going to copy everything from there, copy it to this position, so that at least we get a different view. In this case I'm going to move the datum ground level by, say, 200, right, below. And what we're going to do is, in this case I'm now going to annotate to show you the soil cover. In this case it'll be from this position to the top of the base, which is in this case 1300. So you're going to MA 1500, put this as 1.3. So what you will do then is then come to soil cover and put in 1.3, and as you can see it is clearly shown there. If we use 1.5 it was going to cover everything, but in this case we're going to use 1.3. Now the next thing that we need to move on is to look at the materials section, which we now need to input. So next up, once you're done with inputting your geometry input, that is from the length of the base, the column, and then for the cell depth cover, and also the depth of your base and the stub column height, the next thing you need to focus on is the materials input and properties section. So the first thing it will ask you is, what is the density of your concrete? So using the code that you use, whether it's BS or depending on what code you use, well, normally the average is usually 24. Now on most, whether it's ACI, SAPS or PS, but I'm just going to go with 24. Then the soil density, remember this is obtained from a geotechnical report that you get from the geotechnologist or anyone who does the soil investigations for you. So what you will need to do in this case, what I'm just going to assume an average a loose sand soil density of 18, because that is what is mostly found sub-Saharan Africa. Even if you go to England, this is what you will find in most areas. But then remember, this will depend on what you actually have on your site. So please don't just key in 18. Make sure you look into geotechnical report, see what the geotechnical investigator says, and then put in. Next, you have the soil friction angle. This one is the internal friction angle for calculating the passive soil stress. This is also obtained from the geotechnical environment report. But I'll tell you, from sub-Saharan Africa and dealing from where I am currently right now, the average angle is about 20 to 25. So I'll use an average of 22, which is what we will use for now. Now, the next thing that you would do is the coefficient, right, for calculating horizontal friction between the base and the soil. This is also dependent on your geotechnical investigation report. But for soils that usually have a density of 18 and 22, what you usually find is this will be 0.5. So this is what we will put in. Once you've done this, you've put in the materials input data, and the next section you now need to put in is the reinforcement characteristics that you expect for your base. So for the reinforcement characteristics, what they're just trying to say is you need to specify the concrete cover to the reinforcement. So a lot of things will determine the cover that you will put, depends on the exposure, the code, and everything that it will say. So for them, in this case, whether it's the British or the South African, we can use the South African because it is derived from the British code. What we'll do is, in this normal case, what you would normally find is the cover will be normally 50, right? If we expect a mild exposure, and even when it's in the ground, I'll try and pull up a section that shows you where it is coming from. This is from the general conditions of contract where it deals with concrete cover. The section will be put up on the screen. Now, so in this case, the default you see, what you would want to do is normally you're assuming 50. That is in the X. So remember, the X layer is always the first one. That is the first layer. That will be at the bottom. Then the Y layer is the one. That will be the layer after that. So either the top or the bottom, it will be the same thing. The first layer is the X. Then the next layer is the Y. So what you would do is, in this case, if it's 50, then you're going to assume your bar length of diameter. you could say 10 because the minimum bar you put in a foundation is a 10 millimeter diameter. So that would mean the next layer would be at a depth of 60. Now, same applies when you're using from the top and the bottom. It's just a matter of repeating 50, 60, 50, 60. In the case you'd put 75 plus what would you say, 75, then this one would mean you'd be at a depth of say 85. So you might have to automatically key in this, right, manually I mean. So in this case you would also put 75 and then you would put 85. This also depends on the conditions of contracts. So for now we can use 80, 75, 85, 75, 85. But if we expect them out closure, we can use 50. And in this case, sorry, this will be 50. This will be 60. This would be 50. And this would be 60. So this is it when it comes to specifying the reinforcement cover that you need. So in this case, next thing that you would now need to do is to look at the stability criteria which you need to state. That is to say the relevant limits that you want when it comes to checking for overturning, slip, bearing pressure at serviceability and ultimate limit state. Setting the stability criteria is quite easy. All you have to do is remember the first thing that it will ask you is the ultimate limit state when it comes to overturning or self-lift, right, when it comes to self-weight. So normally what you would do when it comes to the ultimate limit state, you can get this from the code, right, 0.91 or 1.1. In the case where you use 0.9, you are saying that even the list, this is where you really want to be conservative. But in the case where you want the self-weight for overturning or you to design using a large factor, that would mean that it will overcompensate for the turning moment. But in the case if you go to 0.9, this is the much safer side. So most people, when they're still beginning and they're not too sure about what they're doing, they will choose 0.9. So in this case, we'll choose 0.9. Now, the ultimate limit state living factor when it comes to self-weight as well. Now, this one depends on the code. In this case, it now depends. If it's BS, it's going to be 1.6, so you want to put 1.6. But even if you're using South African codes, it's going to be 1.6, so you would want to use 1.6. Now, the next thing, which is not really stability as such as well, but it's also a property of the soil material, is the maximum serviceability limit state bearing pressure. So this will be the maximum bearing pressure that is allowed or that you can obtain from your soil. In most cases, the safest bit that you would want to use is 200 because the average bearing pressure for even the worst type of soil is 250. So most people will go with 200. If you want to go with 100, you can do that, but that just means the area of your foundation will increase and your design will not be economical. But the best thing is that is why they tell you to go and do an actual source report, so that in the case you may try and have your foundations at a depth that allows say 500, 750 or 1000, because once you get the bearing pressure of about 1000, this means the area of your foundation will greatly reduce and you save cost of the concrete. All you'll just be doing is having people excavate to a deeper foundation, and this just means more money for labor as opposed to for steel and concrete. But remember, steel and concrete always costs more than your labor. So in this case, since the average is usually 250 or below 100, so we're just going to be putting 250. This is for loose sand, which is low bearing pressure, and the modulus K modulus of about 4.8. Next, what you will need to do is the self weight or the self factor, safety factor rather, sorry. SF is the safety factor when it comes to overturning at the ultimate limit state. So same applies. This happens if you go with 1.6 or 1.7, you really need to know what you're doing. But if you really want to be conservative, you would want to go with the lowest factor, right? What is the safety factor in this case as well? For slip, you might want to go with 0.9, but most people, what they do is just go with what is stated in the code. If it's South African, it's 1.2. And if it's going to be 1.2, if it's going to be the British code, it's going to be 1.4. In this case, it's going to be, let me check, 1.4. If that is, if you're using BS. In this case, we're using BS. We might want to put in 1.4, 1.4, and we get to go. Now, for the FCU of the base, unfortunately, since we're in demo, this is limited to 15, but this one is saying 19. It all depends on what is happening or there's a glitch in the system. So this will always be limited. You'll be unfortunately be unable to use it or change it. So you will need to activate your license and get a license. So you can always contact Prokon Software Consultants, which I want to say I do not work for, I don't advertise for, I do not get paid for by Prokon Software Consultants. So please, I'm not maybe the best person to talk about the license. Now, the next thing that you would want to do is the FCU for the columns. Now, fortunately, this one is you can change, but then it doesn't really make sense if you're going to change this but then for the FCU for the 19 is going to be the same. But at the same way, you might want to keep it in demo in 20, and go to 25. If you're going to 40, you're pushing it, it's really not going to be necessary. Then last but not least, you have FY, which is the CU strength of your tensile strength of your steel. In this case, you can use 450, 460, depending on what the code says or what you actually have on site. If your code says 460, but then the steel you have is giving you 410, makes no sense for you to design for 410. For 460, I mean, it's rather best you design for what you actually have, which is 410, because you don't want to overstate the actual strength of your steel. Now, as you can see, it's telling us we don't have any loads entered. So what we're going to do is we now need to look at the loads or what load cases you need to enter and understand that, so that we don't say we're wrapping the video. Let's just continue and finish with this section before we move to the next section. Now, the next thing is when it comes to entering your loads, one thing you need to understand is you can enter one or more load cases, but the following should be kept in mind whenever you're entering your loads. So remember, the first thing is all the loads that you're going to be entering are going to be applied at the center of the column, and a column is positioned at the center of the base unless values of E and F are entered, and we talked about that, right? So what we're going to do is this is going to be quite easy, right? The first thing is you enter all the loads unaffected, and you always need to specify what load case it is, and in this case you can always even have so many loads for one particular load case. In this case, what you would want to do is, let's say for this one, this is going to be load case 1, and it's going to be the dead load plus the live load, right? And in this case, this is going to be just the dead load, and the last one is just going to be the live load. Now, this is what you do. This is to make you remember what it is and what it is. Next, what you would do is specify the column on which that load is going to be acting. In this case, we only have one column, so you will choose 1. Then when it comes to 2, also remember that you're going to put 1 there. I'll show you why I am doing this. Then you also put 1. Then in this case, also specify for 1. Now, LF ULS over T, all you have to go back is to come to this point where it says ULS for self-weight over turning. In your case, what you're going to do is you're just going to put 0.9, right? And just copy this, because this is going to be the same. Then the limit factor when it comes to the ultimate limit state, remember, it's this one. And wait. This is the limit factor. This is for ultimate. Yes. Sorry about this. This is supposed to be 1.4 since we are using BS. Remember about that. This is going to be 1.4, which is when it comes to self-weight. Now, this is where we're going to put the live load and the dead load. So whenever you put in the live load, that will need to change to 1.6. And in this case, this also changes to 1.6. And this changes to 1.6. And this changes to 1.4. Because this is strictly going to be dead load, this is going to be live load, this is strictly going to be dead load. Then the next thing is you'd want to put the load. So what we're going to assume, we assume the column was taken a total of 100. So what we're going to assume is it's taken, this is what we'll do. We'll just assume it's going to take 50 of the dead load, or rather 50 of the dead load, which will then multiply later on. And let's just say it is going to take about 30, and then the extra 2, which makes the 100, will be after factoring, right? So this is the same applies. So in this case, this will be 50, and then this is 30 alone. And remember, for this example, we're just doing actual load, so we're not going to put anything else. So this is how you would enter your load. So in the first load case, you're just saying that for column 1, it's going to have a load of 50, which is going to be multiplied by 1.4 and 0.9. Then this one, 1.6 and 0.9. And in this case, 50, 1.4, 0.9. When it comes, this is for stability. This is for bearing pressure. Remember, this column is for checking for the stability, and this one is checking for the bearing pressure. Now, so this is how you enter the loads. As you can see, you can put as many load cases as you want, and you can even combine so many columns or rows under one load case. If you wanted, you could say insert. And in this case, maybe you want to divide even this one into 2. You could say C, then V, then this will be 1.4 is also C and V. And this one you could change it to 25 and then change this one to 25. It would still have the same effect, right? It's still loaded under the same load case, so it will apply. Then last but not least, you would want to look at optimize. In this case, you would want to deal with the cost of concrete per cubic. In this case, we will go with $115 per cubic. And per ton for steel, I remember it was around 92, if I'm not too mistaken, or it was actually, it needs to cost more than this, the concrete. So I'm not too remember. It must have been 92 and 115. We'll double check this. Maybe in the next video, I'll put the correct values when I Google them. Right now, I don't have my internet. Now, the last but not least, you might just want to say this is tutorial. In our case, we are tutorial 10. So let's just make it tutorial 10 base. And we're good to go. So what we're going to do is we're just going to save it here. Save as. And say tutorial 10 base. Now, once we save it as this, what we're going to do is we're going to wrap up the video at this point. Now we have an understanding of how you input the loads. The next thing we now need to look at is the interpretation of the design. And also we also look at some of the theory that goes in when you check it for stability and ultimate limit state bearing pressure, and also how it provides the still for you and some of the things that you need to look out for. So that will be done when we click on the design tab. But for now, we need to wrap up the video, and I'll see you in the next tutorial.